in Cupertino. Bill, PGO. Hey, good morning, Billy.
Quick question.
All right, quickly.
Question was, which is clear off the subject, but if you bore a hole through the earth, what is the air pressure at the center of the earth?
It's not easy. You have to do a little calculation. Okay, hold a second. You asked me a question. I put my brain in gear. Okay. The gravity force decreases as you go in towards the center of the earth, but the column of air above you increases, doesn't it?
It seemed to me you'd have to do some type of a...
You have to do a little integration. And it isn't straightforward, but look, you have 200 miles of air above us now.
Yeah.
But you have the gravity force of the full Earth is impinging on it. If you went to the center of the Earth 4,000 miles, then that'd be 20 times, well, you'd have 20 times as much volume, but the mass would be less as you go down because the gravity force is going down.
In other words, at the center, it would almost be like in outer space if you had a roof.
At the center, if you had a confined column, it would be greater than it would be standing on the surface of the Earth.
It's coming from both sides of the Earth.
Yeah. Oh, wait a minute. You want a hole clear through the Earth. Oh, that's a different problem. I'm sorry.
What?
You get a hole clear through the Earth, it's going to be, you'll have the same pressure on either side. What's wrong with me?
Well,
Hey, look, that's all we can do with that here on the radio, huh?
Think about it and work on it.
Well, just simply take a unit volume of air at each point on the line on the column and take the gravity force, which is the inverse of the radius.
Right.
All right, and integrate that and you get your answer.
I can figure that.
All right. Hey, Bryce and Cooper.
Yeah, hi, Bill. This is Paul.
What's on your mind?
Hey, I heard your answer to the 9-year-old earlier about the gravity with respect to the mass
Yes.
of a planet. And I was wondering why, when you get close to the center of the Earth, what is the value of gravity at that point? And basically, why is that value as it is?
Well, what do you mean, what is it is? If you know what it is, fine. Well, what happens as you go, if you were to drill a clean hole through the center of the Earth, all right? Let's do the equivalent of coring an apple, all right? Shoving a clean hole clear through it. As you went down towards the center of the Earth, you would experience less and less force on your body. Weight, in other words.
But you're getting closer to the center of the Earth?
You're getting closer to the center of the Earth because there is mass now above you that's attracting you, as well as mass below you, isn't there?
So you're saying...
The mass above you is canceled out, effectively. And as you got to the center of the Earth, you would feel no force. This is ideally now. If we had a perfectly round, homogeneous globe for the Earth. So if you got to the center of the Earth, there would be no net force on you. Okay?
Gotcha.
Now, as you move farther and farther away from the center of the Earth, there is more and more mass beneath you. In the sphere that is beneath you, there's more and more mass there, isn't there? And so there's a greater force on you, gravity force on you.
Okay.
But the mass above you, that is in effect represents the sphere that you're trapped in, there's no net gravity force to it on you.
So it would be actually pulling you up then?
No, there's just no net gravity force on you.
Because?
Well, what I'm saying is that the net force on you is equal to the sphere of mass beneath you at any given point on the radius as you come out. Now, you can look at it lots of different ways. You can say the mass above you is pulling on you, and the mass on the other side of the Earth is pulling on you, and the mass under you is pulling on you, and you balance all these forces, and you come up to what I just told you.
So basically it'd be zero at the center of the Earth.
Zero at the center of the Earth.
Good enough, Bill.
If you drop, put it this way, if you had a ball bearing and you dropped it down this shaft that goes clear through the Earth, the other side, it would accelerate going down until it hit the center of the Earth, and it would have a very high velocity, and then it would start to decelerate as it goes out the other side until it got to the other side of the Earth, and it would stop. And they would fall back down the hole and start over again. You'd have a pendulum, in other words.
Would that be a professional motion machine, Bill?
No. Well, ideally, but God, I mean, all the things that you can't ideally achieve. You can't achieve a clean hole through the earth. You can't.
Well, actually, that sounds pretty good. Cause,
perpetual motion, in the sense, no, it's no more of perpetual motion than a pendulum. You've seen a pendulum swing, haven't you?
You're right.
All right. Well, the ball going through that hole in the center of the earth happens to be controlled by the same forces and the same motion equations as a pendulum. In fact, that ball going through the center of the earth will have a period. Hey, I never thought of this before. It'll be the same as a satellite. The ball, if you put a satellite in near Earth orbit, very close to the Earth's surface, its period of revolution would be the same as the period of
the surface of the Earth.
No, as the period of that ball bearing going through the mine shaft. See, I never thought of that before. About 90 minutes. Goes down and back in 90 minutes. Thereabouts. Okay? Take care. Stan in San Jose, Bill, KGL. David in Berkeley, Bill, KGL.
Hi there. I really appreciate your program. This
thank
is David from Berkeley. I had a question about the young boy raised a question about gravity, and I had a question in my mind long time. I just wanted to bring it up. I know that other types of forces, like electromagnetic forces, are basically mediated by some sort of particles, like by photons. I was wondering, what about gravity? Is there a particle that mediates the transmission of this force between different...
Well, you have to realize that all of these things you talk about, when you talk about photons and particles, are theories. We've never seen one.
Right.
Experiment is consistent with theories of the particle or wave nature of light. Many of the theories, the most accepted theories, the closest approximations, let's put it that way, to unified field theories,
right,
utilize the concept of particles in terms of transferring fields.
Exactly.
And so it's a fiction, but it's consistent mathematically with what we observed.
Okay.
But there is no complete unified field theory as yet. It incorporates gravity with all the other forces.
So there is no such a particle?
Well, we don't know.
Okay.
Well, we've never seen one.
Okay.
We've never seen a photon either, you see.
Right, but is it correct to assume that similar to other types of forces, and it takes time for gravity to be transmitted?
Yes.
It is not an...
Yes, no, that's known.
Okay.
No, that part is known.
Oh.
And, but how and what exact form it is and what's consistent with the other forces, that's the main holy grail of nuclear physics, of basic physics.
Okay.
Of the theoreticians. The common belief is that there will be a particle nature of the gravity field.
Okay. So if for example, by some force we could take the sun away, we would not feel the removal of gravity from Earth for like a few minutes, right?
For 8 minutes.
Okay. All right.
Thereabouts, 8 minutes.
Okay.
All righty? Hey, take care. KGO time now is 11:39.
Yeah, hi.